Hello and welcome to Chapter 3. We're going to be talking about frequency distributions. So in Chapter 3, we're going to be talking about stem plots, frequency tables, and additional frequency charts. So the first thing we're going to start off with is what's called a stem and leaf plot. We want to start by looking at data with graphs and plots and charts and kind of get a visual representation of the data we're looking at. This is always the best method to always definitely look at data in a visual form as opposed to just like a bunch of numbers in front of you. So one of our favorite techniques at looking at single variables is the stem plot. I believe this is more of a sardonic type phrase here. It might be some people's favorite. I definitely have and prefer others, but nonetheless, it is definitely a technique to look and use. A stem plot is a graphical technique that organizes data into a histogram-like display. So it's going to look like a histogram-like display, and we'll be going over the difference between histograms and bar charts and pie charts at the end of this chapter. And once again, it's just a great visual representation, which is what we're trying to do. Sometimes we can see things a little bit better in a graph form than just the numbers right in front of us. So here we're going to go over a stem plot illustrative example. So we're going to have a simple random sample of 10 ages, and then we're going to list the data in an ordered array. This is very important. Anytime we're doing stem and leaf plots and moving forward, we're definitely going to want to always put things in an ordered array. This will help definitely for Chapter 3 and Chapter 4 and moving forward. We want the data to be in an ordered number from least to greatest. This will help us when we're doing our 5-point summary, finding inner quartiles, median, all these different statistical techniques used. It's very important that they're in an ordered array. If they're not ordered, then you cannot really do these things properly. So here we have our data. So we have our 10 ages from 5 to 52, and you'll notice that they are in ascending order from least to greatest. What we're going to do is we're going to divide each data point into a stem value and a leaf value. And the way we do that is, for this particular example, we're going to take the tens place will be the stem value. So remember, if you can kind of see here, so you have your ones and then your tens place for each significant figure. And here the tens place will be the stem value and the ones place will be the leaf value. So an example, if we had the value of 21, the stem will be 2 and the leaf will be 1. Moving on to what this actually looks like is here we have our illustrated example. So we have an axis of the stem values, so that will be shown here. So these are our stems, and then our leaves are going to go this way in order. So remember, everything has to be in order, so you're going to go from your least value to your greatest value for your leaves. So if you had 21 still, you're going to place the 2 for the stem, and then the 1 will slide down right next to it, and that would be your 21. Another thing to notice is your access multiplier, right? So think of the line here kind of like a decimal, and if you were to take 2.1 times 10, you would get your 21. Just let you think that for a second. And the access multiplier can be anything you need it to be in order to make the stem work. The important thing to know is the access multiplier has to be consistent throughout the entire stem plot. So if you use 10, then everything has to be a multiple times 10. So here, when we put all the data points in this stem and leaf plot here, this is what it would look like. So you have your stem and your leaf shown here, and then you have your access multiplier. And this is what it looks like. And then once again, just remember that everything has to be in rank order. So when you have so let's go to our 20s, right, or our stem of 2, and then our leaves here. So you know this is going to be 21, 24, 27, 28. Notice how they're in rank order. You can't just put them as in like 2, like 4, 1, 8, 7. That doesn't work. They have to be in a ranked order or ascending order. And then for horizontal purposes, because once we kind of rotate it, what you're going to kind of see here is a histogram chart. in a very simplistic form, but if you rotate sideways, it kind of starts to display a histogram chart, and that's what the stem and leaf pod will eventually kind of turn into, and you can use it for. So now that we have a stem plot, we want to interpret it, right? Because like we said, when we have the stem and leaf plot, it's a great way to visualize data. Now we can see it. What does it mean? We got to interpret it, right? This is supposed to help us interpret it a lot quicker and easier. So when we're interpreting stem plots, there are three aspects that you want to look at. First is the shape, then the location, and the spread. Not necessarily always in that order, but those are the three things we're going to be looking at. When we go through the book and they ask you to describe stem and leaf plots, they're looking for you to describe it based on its shape, its location, and the spread. So when we look at the shape, when we're interpreting stem plots and shape, we're looking at the symmetry of the stem and leaf plot. We're looking at the modality, which is the number of peaks, and the kurtosis, which is the width of the tails. Or another way to think about it is the outliers in the tails. So when we have shape refers to the pattern when plotted. So here's our data, and once again, this is our data, but we just have x's here, right? So we're kind of given the silhouette view of it. There's no actual numbers, but you can look at it in kind of a visual form. And when you're looking at this, you want to consider the symmetry, the modality, and the kurtosis, right? So we see it kind of peaks up here. This would be potentially the modality. It's not very symmetrical, and there's not a lot of excess stuff on the side, so the tails are not going to be very long. When you have a histogram overlying curve showing distribution shape, so here's a histogram, right? This is number of individuals and what probably appears to be like an IQ score or some sort of standardized test score. And what you can see is you have a normal distribution or a bell-shaped curve, which a bell-shaped curve is going to be symmetrical, right? Symmetrical meaning if you were to cut it in half, it's going to be even on both sides. Sorry, my lines aren't very straight. It is what it is. I'm horrible at drawing. But nonetheless, it's symmetrical, even on both sides. Other examples of shapes, so once again here you get symmetrical. Then you can have another shape that could be symmetrical, but it's not a bell-shaped curve, right? Part B is not a bell-shaped curve here. Here we have a symmetrical uniform, right? It's very uniform. It's kind of a box shape. It's symmetrical because it's even on both sides, and it's uniform. Where then the part D here we have an asymmetrical and bimodal shape. So here we have another example. One thing to look at is what we have positive and negative skews on shapes. So as you can see here, letter E is a positive skew and part F is a negative skew. One thing to always remember, this is a helpful thing that I recently found out, is if you look at your feet, right? If you look at your right foot here, and you kind of can see that your right foot, it's greater towards the left of like an axis, and then it curves down, kind of like a positive skew. So if you think of your right foot as a positive skew with your big toe being towards the left axis here, that's a positive skew. And if you think about your left toe, where the big toe is towards the right of the axis, then that is a negative skew. So if you remember your left foot as negative and your right foot as positive, that'll help you see the shape of positive and negative skews. Modality, number of peaks. So the number of peaks a graph has, unimodality 1 peak, bimodal 2 peaks. And then we have kurtosis. Kurtosis, once again, is kind of judging the outliers in the tail. So we have a mesocuric right at the top left here, and that would be what we would consider more of like a bell-shaped curve, a normal curve, where everything's evenly distributed. Next to that, we have a platocuric, where in the platocuric it's kind of fat. It's kind of it's kind of more spread in the middle, and the tails are kind of very short. Short on the sides here, and then we have leptocuric, where it's very centered information, and the tails are very long on the sides, right? On the sides here, they're very long tails. Kurtosis is not easily judged by the eye, so you definitely have to graph this out and look at it. You can't just look at numbers and determine if there's kurtosis based on just the numbers. It definitely has to be kind of graphed out and looked at. One way to kind of remember kurtosis, and this is from a very old book, and there's a very specific way to determine kurtosis that our book doesn't go into, which this paragraph kind of talks about here. But nonetheless, the way they're trying to describe it still works, where if you have platycuric curves have shorter tails than the normal curve, right? And so that's shown here kind of with the platypus. And then if you have leptocuric, you have longer tails. And if you think about the kangaroos here, kind of forms more of a leptocuric type graft. And if you think of leptocuric as kangaroos can leap around, this might be a great way to differentiate them between leptocuric, platycuric, and mesocuric. Next on location, we have the gravitational center, which is the mean, and then the middle value is the median. So when we have a location of mean, we have the eyeball method, which you can visualize where on the plot would be where the data would balance, right? Where the middle point of the balance, the arithmetic method, is to sum all the values and divide by n. This is shown, I'm going to show you. There's two ways we can find the average. So there's what we have up top, which is x bar, which is the sample average, and then we have mu, sample, and then we have mu, which is more of a population average. So for here, most of the time we're going to be dealing with x bar, and if we want x bar, it's going to be adding up all the values and dividing by n, right? The sum of all the values divided by n. Well, we know n is equal to the total number of people in the sample, and we want to sum up all the values. So this would be equivalent to adding up your x of 1 plus x2 plus x3 all the way to your x of n value divided by n, the total number of people. Another way this you can look and see this is the sum, so capital sigma of x sub I divided by n. The sum, capital sigma, you'll see this a lot more, capital sigma, the sum of all the x values divided by n, the number of people in your sample. You would use the same thing for population. We just would say, we would represent that as mu, and that's how we determine if it's population. So you sum all the values and divide by n. So here we have our data, and then you can kind of see where the gravitational center would be. You can kind of eyeball it. It's not great. It takes practice definitely to do. And if we were to add up all the values here, we get a sum of 290 divided by the total number of 10, and we would say the mean or average is 29, or x bar equals 29. And then we have the median. So here we have an ordered array. This is very important. For a median, you have to have an ordered array. If you don't have an ordered array for the median, you're not going to find the median. It has to be an ordered array. And the way we find the median is, one way we can do it is by finding the depth. Now the depth doesn't tell you what the median is, it just tells you how deep in this array the number is. So the median has a depth of n plus 1 divided by 2 on the ordered array. So when n is even, the average points adjacent to this depth. Remember, depth just tells you how deep in the ordered array you have to go to find the median. So for this illustrated data, you have n equals 10. The median depth would be 10 plus 1 divided by 2, or 5.5. So you would go in, so 1, 2, 3, 4, 5, 6. Well, 5.5 is between 5 and 6. So we'd say the depth is 5.5, but the median will be between 27 and 28, which we're going to learn that we add that up and divide by 2, and so the median is going to be 27.5. Chapter 4 has more detail regarding the median. We're definitely going to be getting into more of that when we get into our 5-point summary. Okay, I'm going to stop the video there due to time limits, and we'll pick back up talking about stem plot spreads. Have a good day.